Hello everyone. In this video we are going to discuss practice exercise 2.1 for its second part, because in the previous part we have discussed or we have converted the given vector into a cylindrical form. Now here in this video we are going to convert your given vector into its spherical form. Uh, so we are going to start with what is given to us, and then we are going to move or we are going to see what are the necessary expressions that we are going to make use in order to convert that rectangular system or Cartesian system into its spherical form. So very firstly, we are going to write what is given to us. So we have this given vector q in its Cartesian form, and we are going to rewrite that vector q in its standard form. So what is that standard form? So that will be your given vector q having some component of that vector q along x direction, then it have some component along y direction, and then it will have some component along the z direction. Now, if you compare or if you see your given vector, so there is no ay component over here. No ay component is what? We have the zero ay component. So this given vector q, it reduces to what? We will have that given vector q is equals to component along x direction only and component along z direction only. So we are going to assign equation to this one. So this is your very first equation, that is given vector, and this is your second one that we have found out. Now if you are going to compare these equation 1 and 2, now by comparing this one, what we are going to find out, what is the value for that qx and qy, sorry, not qi, for qz. So comparing equation 1 and 2, we get, so what value we are going to get for that qx? So for that qx, we will have that qx is equals to square root of x square plus y square divided by square root of x square plus y square plus z square. So this is what we have for that qx. Now what to do with this qx? So since we are going to convert this Cartesian system into spherical one, so we are going to make use of some expression. So what are that expression that I am going to put it over there for your reference purpose? You can note it down. So these are the two expressions that we are going to make use within this numerical, where we have that r is equals to square root of x square plus y square plus z square, and that theta, that is equals to tan inverse of square root of x square plus y square divided by z, and this phi, that is tan inverse of y by x. So what exactly is this? If we have the coordinate system in its Cartesian form, where we have the values of that x, y and z, then it shows you that you can convert that Cartesian system into a spherical one. So this is what it is, the conversion of that Cartesian system, Cartesian to spherical one. You can convert that with having the values of x, y and z, and this is the vice versa. That means what? If you have the values in terms of that r theta and phi, that means if you have the spherical values, that is for its r theta and phi, then you can get the values of that Cartesian system, that is x, y and z. So we are going to make use of that two expressions over here. See, this is just for your reference purpose. It is not expected that you should write this whole thing in your theory exam. So I am talking from the theory exam perspective. Okay, now we have that qx, and we have the values of that x square plus y square plus z square. Now we are going to put that values over here. Now very firstly, you can see that we have the numerator, that is to be square root of x square plus y square. So for your we are going to write that for now as it is, square root of x square plus y square. Okay, fine. And then we have the value for that square root of x square plus y square plus z square. So what is that value? You can see over here we have that values to be that r. So this is the value that you can directly put over there. So we are going to put that values of that square root of x square plus y square plus z square, that is equals to what? That is r. Now next thing, for this numerator. So for that numerator, you can refer to the cylindrical system. again I am going to rewrite for your reference purpose. So in cylindrical one, what value we have? Cylindrical system. Within that cylindrical system, we have that rho is equals to square root of x square plus y square. But in spherical one, what we have for that rho, you can refer your theory book for this same. So that rho is equals to what? We have that rho is equals to r sine of theta. Okay. So you can put that value of that rho over here. So what is that rho? Rho is nothing but square root of x square plus y square. And what is that square root of x square plus y square? So you can say that that is equals to r sine of theta. So you can say that square root of x square plus y square is nothing but what? R sine of theta divided by this r and this r and this r. It will get cancel out. So what is left? So we have that qx is equals to simply r sine of theta. So we have that qx is equals to not exactly r sine theta. Sorry for that. This r and this r it will get cancelled out. So we have that qx is equals to only sine of theta. So this is the very first value that we have by putting that values of square root of x square plus y square plus z square. See, if you have any confusion regarding this, why this r sine theta is over there for square root of x square plus y square, so you can put the values of this one over here, so that you can get the values of that uh, this one. So that rho is what? Square root of x square plus y square. So that rho is what again? Rho is equals to r sine of theta. Okay, so with practice you can come to know about that one. Now next is we are going to find out what is that value for that qz from your by comparing that equation 1 and 2. So if you are going to compare that equation 1 and 2 and if you are going to write for that value of that qz. So what is that qz? So you will find that qz is equals to what? Minus yz divided by square root of x square plus y square plus z square. Now what is that y value we have? So for your reference I am going to bring back that expression nearer to this one. Now we are going to put the values of that y and z over there. So what is the value of that y from this expression? So we have that y to be what? R, sorry, that y is what? R sine theta sine phi. Then we have z. So z is what? Z is r cos of theta divided by square root of x square plus y square plus z square. So we have that square root of x square plus y square plus z square is equals to what? R, and this minus sign over there. Okay. Now this r and this r it will get cancelled out. So what is left? So we are left with the value of that qz which is equals to minus r. So this r is from over here. Okay. So you can take any of the r. So we have that qz is equals to minus of r sine theta sine phi cos theta. So this is the value for your qz. Now we have the value of qx and now we have the value of that qz. So we can put the value of that qx and qz in your this equation number 2. So we are going to put that values of that qx and qz within your equation number 2. So what is that equation 2? So we have that equation 2. I am going to rewrite again it for you. So we have that vector q is equals to magnitude along x direction for q and magnitude along z direction for your q. So this is your equation number 2, and after putting that value of that qx and qz in that equation 2, so we are left with that vector q to be sine of theta ax minus, because we have that qz to be minus of this value, so that will be what now, minus of r sine theta sine phi cos theta, and this is it. So we have, this is as your vector q. Now we are going to make use of coordinate system transformation table onto this your vector q. Again, I am going to say that my handwriting is not as good as yours, so kindly adjust that one. Okay, so we have this as your vector q in somehow in its spherical form as well as somehow its Cartesian form. Now we are going to convert this vector q completely in the spherical coordinate system, for which we are going to make use of the some transformation table. So for your reference purpose, I am going to put that transformation table in the next slide, and then we are going to simplify that one. So we have this table for converting that spherical system into Cartesian one, or and vice versa. Or you can also make use of this table for converting that Cartesian to spherical one or spherical to Cartesian one. Okay, so if you are going to rewrite for your given vector q in its spherical form, so spherical form of that your given vector q will be like this one: spherical form of vector q, that will be equals to what now? So we have that vector q having some component along r direction with its unit vector r, then component along theta direction with unit vector theta, and component along that phi direction with its unit vector a phi. Okay, so this is what we are going to finding, or this is what we are going to expect from this conversion. Okay, so very firstly we need to find out what is that QR. So QR is what? You can refer my previous lectures for this one. So this vector QR, that will be what now? So this QR, it will be equals to your given vector Q having some component along the r direction. So that will be like this one: given vector Q having the dot product with AR. So what is that vector Q? We have that vector Q to be sine theta AX minus r sine theta cos theta sine phi AZ having dot product with AR. Okay, so this is what this your vector Q is nothing but that vector that we have found out earlier. Okay, so now make use of the dot product table. So for your reference purpose, I am going to write that sine theta as it is, and then we are going to see what is the dot product in between that AX and AR. So we have this AX over here which have the dot product with AR. So the dot product in between this AX, sorry, so dot product in between this AX and this AR is what? We have that value to be sine theta cos phi. So write that over here. So the dot product in between that AX and AR is what? Sine theta cos of phi. Then minus, write that component as it is, minus r sine theta, then cos theta, then sine phi, having the dot product in between that AZ and AR. So the dot product in between that AZ, this over here, and this AR. So the dot product in between that AZ and AR is what? We have that to be the cos of theta. Now you can have that multiplication. So we have that value of QR. So QR will be equals to what now? Either way, you can take the sine theta as common, or you can write that sine square theta. Anyway, so we are going to write that to be the sine square theta. That totally depends on your practice. So you need not have to bother about that one. So sine theta is what? Sine square theta. Then we have this cos phi, then minus r. So again we have that sine theta, sine phi, and this cos theta. Cos theta is what? Cos square theta. So we can write this as it is. R sine theta, then this cos square theta, and then what is left? That sine phi. So this is the very first component along R for your vector Q. Now in similar way, we are going to find out what are the components along theta and phi direction by making use of this table. Now next is we are going to find out what is that Q theta. So Q theta will be what now? Your given vector Q having the dot product with unit vector along theta direction, that is A theta. So rewrite that one for your vector Q. So we have that vector Q to be what? Sine theta Ax minus sine theta cos theta sine phi is z, which have the dot product with respect to A of theta. Now go for that multiplication by having the reference of that transformation table. So we are going to write that sine theta as it is, the dot product in between that Ax and A theta. So dot product in between this Ax and this A theta. So we have that value to be what? Cos theta cos phi minus this will be as it is, that r sine theta cos theta, that sine phi. Now next is what? The dot product in between this Az and A theta. So dot product in between that Az, this, and this A theta over here. So that is what? Minus of sine theta. So write that one. So for this I am going to write this simply, this sine theta over here, and this minus sine and this minus. So it will be plus now, and this is what we have the component for that theta. Okay. So we have the value for that Q of theta. Now in similar way we are going to find out what is the value for that Q phi by making use of this reference table. Now that Q phi will be what? Q phi will be your given vector Q having the dot product with unit vector along phi direction. So this is what? So again write for that vector Q. So vector Q we have that to be the sine theta Ax minus r sine theta cos theta sine phi Az, which have the dot product with respect to your that A phi. Now have that multiplication. Meanwhile, I am going to write it for you. So this sine theta will be as it is over here. Dot product in between that Ax and this A phi. Dot product in between that Ax and A phi, like this one. So we have the dot product in between that Ax and A phi to be what? Minus of sine phi. Instead of writing it in bracket directly, we can write it like this one. this sine theta will be as it is. With practice, you can have that one. Okay, so don't worry about that one. So dot product in between that ax and phi to be what? Minus of sine phi. Then for now we are going to write this term as it is, that is minus of r sine theta cos of theta. Then this is sine of phi, and the dot product in between that az and a phi. So dot product in between this az and that a phi is equals to what? 0. Okay, I haven't seen that one, or else I have directly written that to be the 0. Okay, fine. So for your reference purpose, you can say that one. The dot product in between that az and a phi is equals to 0. So again, rewrite that one, q phi. So we have q phi to be what? Minus of sine theta sine of phi. Now we have the values for that qr, q theta and q phi. You can refer that one. Okay, so for now we are going to say this to be say some give equation number to this one. I guess this is equation 3. We can say this to be. Now from this we can write your equation 3 in terms of that r theta and phi for your given vector q. So what is that one? So your given vector q is what we have in terms of that spherical form, that is vector qr ar plus this is what q theta a theta, and this is what q phi a phi. So qr is what? If you have noted it down, so you can write it. Let me refer that one. So qr I have written to be sine square theta cos of phi. Okay, so I'm going to write it that again. Qr is what? Sine square theta cos phi, then minus r sine theta sine phi cos square theta, isn't it? Let me check that one. Yes, r sine theta sine phi cos square theta. Yes, that is r. If you have noted it down, so directly you can write it down. So r is what? Minus r sine theta sine phi cos square theta. This is what we have for your vector qr along r direction. So this is your vector ar plus q theta. Q theta is what we have, that is to be the sine theta cos theta, then cos phi plus at r sine theta cos theta sine phi sine theta along theta direction, that is a theta. This is again over here. Put that bracket, and then what is left? That q phi. So q phi, that value we have to be minus of sine theta sine phi into a phi. Okay, so we have that given vector q in its spherical form. Again, you can rearrange this equation to get some good view. So that vector q is equals to what? So that vector q, so sine can be taken out as a common from this bracket. See, this is completely part of your practice. So if you have enough confidence, then you can write it down. I am considering every viewer to be a beginner, so that's why I am going into details of that one. This is not for my videos are not for intermediate or you can say the expert level. These are the for beginner peoples. Okay, so we have that to be the sine theta as common. Then this sine theta cos pi minus r sine theta is taken common. So what is left? R sine of pi cos square pi vector ar plus what can be taken out from this bracket. So we have this sine theta over here, sine theta sine, sorry, sine theta cos theta, sine theta cos theta. So take that to be common. So we have that sine theta cos theta as a common element. So what is left? Cos of pi from the very first term. Then what is left over here? That will be r sine theta cos theta is taken common. So what is left? Sine phi sine theta, or you can say that to be the sine theta sine phi. Then this is a of theta, then minus, there is nothing to take common out. So what is left? Sine theta sine phi a phi. Okay, so this is the final answer for your given numerical. That is, we have converted the given vector, which was initially in its rectangular form, into its spherical form. So this is your final answer. So if you like my videos, if you are getting some learning from my videos, please hit the like button. If there is any feedback for me, please write it in the comment box. If you found my videos to be useful, so please share it along your group. Okay, so thanks for now. See you in the next video.